Hello, welcome to this video on tachyons. So in this video we're going to be looking at a special class of particles called tachyons. They're particles that travel faster than the speed of light. Now you might think relativity says particles can't travel faster than the speed of light, but the equations of relativity allow for particles that are travelling faster than the speed of light. They just ensure that these particles can never travel slower than the speed of light through a vacuum. So you and I will never become tachyons because currently we're moving slower than the speed of light. But tachyons may well exist in nature and are a valid solution to the equations of Einstein's special relativity, and that's what we'll look at in this playlist. We'll see how for tachyons time and space seem to switch roles, and we'll also see for tachyons that they have a bizarre property that as the tachyon loses energy, contrary to what you might expect, the tachyon actually travels faster. Or in reverse, if you want to slow down a tachyon, you want to actually give it more energy, which is really bizarre, but it's all to do with tachyons moving faster than the speed light moves up through a vacuum, and that's what we'll be looking at in this video. So, to briefly review what is a tachyon, before we look at kind of what kind of space and time looks like, if we will watch a tachyon go by past us. Well, a tachyon is defined to be a particle that moves faster through space than the speed of light through a vacuum. So essentially a particle that is moving faster than 3 times 10 to the 8 meters per second. And all of the strange properties of tachyons are due to it moving faster than the speed of light, at least relative to us. I say relative, because the actual velocity of a particle that you would observe depends on how quickly you're moving. So, for simplicity, let's assume you're stationary watching a tachyon go by, and this tachyon is moving faster than the speed of light. Well, to understand what time and space seem to be doing for this tachyon from your perspective, we have to talk about forward position and the space-time interval. So if you're new to the idea of forward position, essentially forward position is a description of where the particle, the tachyon in our case, is in space and where it is in time. So let's say, for example, at time 0, the particle is essentially where you are. Our tachyon is where you are. But kind of like, let's say, then the particle kind of keeps moving at constant velocity. And in the time interval dt, it would have moved a distance dx. So we can say that the particle is at a time dt and at a place in space dx. And if we put those two pieces of information together, we get where the particle is in space-time, so where it's in time and space. Now, if we were going to kind of like look at where the tachyon is in space-time, we would describe that position with a single full vector. A single vector linking the points of 0, 0, and wherever that tachyon has got to in space-time over a time interval dt. And then that will correspond to a single full vector, so a single one of our straight lines on a space-time diagram. However, if there was another observer moving relative to you, then it would kind of experience a different relative velocity of the tachyon, and therefore that observer would say the tachyon would have moved a different distance, at least relative to them, meaning that they would say that dx would actually be different to what we're saying dx would be. And also because of time dilation, it would turn out that an observer moving relative to you would say that the time interval that has passed dt would be different to you. and therefore different observers can disagree on the components of the forward position of a particle or a tachyon. But any two observers will agree, it turns out, on the size of forward position, and that relates to the core idea of relativity, that the speed of light is the same for all observers. And the square of the length of this vector, this forward position, is given the symbol ds squared. So essentially, we can say that all observers will agree on ds squared, so the square of the size of forward position, describing where our tachyon is in space-time, but they may disagree on the components. But because we've got ds squared is constant, we can just consider different values of our time-like components, so cdt, and our space-like components, so dx, of our forward vector, and then we can plot cdt and dx, and look at different combinations for which ds is some constant, or ds squared is some constant. And that's what I've done in our space-time diagram here. Now, you see that there are kind of four regions present in this diagram. Now, two regions we've looked at before. These are the red regions, if you like. So for the red regions, if we look at any straight line, so any one of our red straight lines, we see that because it's kind of slanted towards the vertical axis, that is, its angle relative to the horizontal is 45 degrees or bigger, we can clearly see that kind of cdt is bigger than dx, and that's to do with the particle travelling slower than the speed of light. So, if we're looking at kind of, four vectors for particles that are moving slower than the speed of light, and the forward vector will lie somewhere along one of our two red light cones. And we call it a light cone because the boundary of the light cone actually refers to the space-time interval associated with, it refers to light itself, essentially. It is our kind of bounds. Now, but that's a kind of like another solution that we haven't really talked about before, which is our blue region. Now, if we look at our blue region, for the light cones, if you like, to become horizontal, so for the forward vector to be slanted towards the horizontal, so in this case the space axis, we require that dx is bigger than cdt, and that has to do with the particle travelling faster than the speed of light. But a curious thing happens with the space-time interval when we insist that dx is bigger than cdt, or v is bigger than c. So kind of like, to get there, if we think back to ordinary particles, so ordinary particles are travelling at a speed less than the speed of light, so v is less than c, which ensures that dx is less than cdt, and therefore ds squared is positive. And we like positive numbers, but also it ensures that ds, which is really the length of the forward vector itself, is going to be a real number, because ds squared is bigger than 0, it's positive at least, it's not negative. So, if we define the space-time interval as we have done here, then ds is going to be a real number, which makes it easy to deal with. However, if we use this definition of the space-time interval, which works great for ordinary particles, but we apply it to tachyons, well, for tachyons, dx is bigger than cdt, in which case ds squared is negative, so ds is imaginary. Therefore, our forward vector has an imaginary length, which is really unusual and very strange. And we'll see that the idea of quantities that are traditionally real for ordinary particles end up being imaginary for tachyons follow us when we look at the connection between the velocity of a tachyon through space and its relativistic energy. So that's a trend we'll see popping up. And essentially all these blue 4 vectors, so the straight blue lines, these straight blue lines refer to 4 vectors, with the same magnitude of the space-time interval as the red vectors, but for which ds, unlike the red vectors, is imaginary. Now, kind of that's slightly mathematical, but a more kind of physically, orientated discussion of what's happening here when we're going from ordinary particles to tachyons is that essentially you can get the blue light cone and the 4 vectors within it by taking the red light cone and the red 4 vectors and just switching the horizontal and vertical components. You essentially reflect the red 4 vector along the line y equals x, and you'll get a corresponding blue vector, for which the size of the space-time interval will be kind of preserved. And so what that is kind of telling us, bearing in mind that the one of our components is the time-like position and another component is the space-like position of our particle, is that essentially for tachyons, kind of if we were looking at a tachyon, it would behave like for it space had become time and time had become space, because it's kind of got, we can go from a 4 vector for an ordinary particle to a 4 vector for a tachyon by just switching the space and time components. Now, a way that physically manifests, we can think of if we, think of the tachyon version, if you like, of a time dilation to an extreme. So, ordinary particles, so by that I mean particles that travel through space at less than the speed of light, these particles can experience something called time dilation. Now, time dilation is where if you're going to look at one of these ordinary particles moving, you would see the faster that particle moved, the slower internal processes would seem to occur for that particle. So, for example, it would take longer and longer to decay. And in the limit, where the velocity is approaching the speed of light, the amount of time any internal processes would seem to take for the particle, according to your perspective, would become kind of infinite. So for an ordinary particle, it can look like to you that time for that ordinary particle is essentially slowing down almost to a complete halt. Such that, any internal process for the moving particle seems to last an infinite amount of time. And also because time is so dilated, it would seem that the particle would, in a sense, react slow and slower to any energy you give it, and would seemingly occupy almost a single point in space. So kind of like for a particle that is moving less than the speed of light, but as it's approaching the speed of light, you as a stationary observer would observe that time processes seem to take an approachingly infinite amount of time. Now for a tachyon, we get a similar kind of thing, but time and space flip. So for a tachyon, you get a similar effect, but it's not time that essentially seems to become infinite, or time duration. It's actually space. I.e. the particle seems to occupy, an infinite volume of space that seems to be everywhere in the universe. And if we look at a 4 vector for such a particle, for one of our tachyons, we can see that we clearly have a 4 vector corresponding to the 4 vector essentially lying, horizontally, such that it, extends across space, but doesn't have any, variation in time across it. And that's the horizontal 4 vector. And this horizontal 4 vector corresponds to a kind of tachyon, which from our perspective would seem to exist across an extended region of space and possibly everywhere in space, but it would do this for a single moment in time. It would be there and gone, because its whole motion, which you can get by just extending the full vector, across the entire motion, time doesn't seem to go up or down. So, in other words, this kind of tachyon, as it's moving, just seems to always exist at the same point in time. And we can kind of call this loosely a momentary particle. It's a particle that exists at a single moment in time and then it's just gone. Now, that may well be one difficulty with detecting tachyons, in that, possibly they're moving so quickly that actually the amount of time they exist for is possibly very, very brief. So, one really cool thing about tachyons. Now, one thing you might wonder, given how strange particularly these things have become, is, can we trust special relativity to apply to tachyons? Because special relativity has really been only tested for particles that have moved less than the speed of light. Tachyons are kind of a speculative extension, if you like. And we always have to be careful when we've got a bunch of solutions, when we've got a bunch of equations where we've tested and verified some solutions to go, well, maybe the universe allows all solutions of these equations to be realised. The idea of having equations and testing them for some solutions, but then looking at other solutions that you haven't tested, is called analytic continuation. Now, analytic continuation is really cool because, it's plausible that it works. But it's worth saying that, we are assuming that tachyons would obey the same fundamental kind of equations of motion, or associated motion in space-time, such as the idea of the space-time interval still being, given as a physically meaningful quantity according to the same relation we had for ordinary particles. Now doing that kind of raises the question, well, maybe tachyons obey fundamentally different equations. But personally, I think, and this is only my personal view, but personally I think, well, a tachyon moving at a velocity greater than the speed of light is still moving at a velocity which is, physically the same kind of quantity as velocity when velocity is less than the speed of light. So I think it's fair to go, we should trust that, if particles did move faster than the speed of light, special relativity would apply to them as well as it applies to ordinary particles, and the fundamental equation should be the same. However, whether we've got the fundamental equations, or whether it just looks like we have, but we haven't looked at special relativity in a broad enough array of solutions to see that there's something more fundamental, is a different matter. But anyway, worth thinking about. But now we talked about kind of tachyons in the context of space-time and four vectors. Let's move on to talking about energy, momentum, and mass. And their strange ability to move faster when they lose energy, which does have something to do with quantities that are real for ordinary particles becoming imaginary for these tachyons. So now we're going to look at the link between energy, momentum, and mass, and look at how energy and momentum are associated with each other. Now it's worth saying in this slide I'll be using natural units where we define c to equal 1 and relative velocities accordingly. Now sometimes here I'll include c because it's helpful for relating the quantities like energy and momentum to equations you may be more familiar with. Such as our expression for the Lorentz factor, or the idea of Rath's mass energy and that kind of thing. But sometimes I'll leave C out. But either way, it's perfectly fine. But worth saying before we get fully going that c equals 1. So sometimes I'll include it, but just to make the equations essentially in their more familiar form, and other times I won't include it. But because c equals 1, multiplying something by c doesn't at all change the thing we're multiplying. So whether we include c or not is just a matter of preference. So if we kind of, just take c equal 1 and ignore factors of c, then we can relate energy, momentum, and the Ross mass of our moving particle according to the equation in the purple box. Now, rel here is kind of what I use to show that something is relativistic. It's just my kind of personal preference for notation. So our equation says that the relativistic energy squared minus the relativistic momentum squared is equal to the Ross mass of our moving particle squared, where the relativistic energy and the relativistic momentum are the energy and momentum we as the stationary observer would associate with the moving particle. Now, this kind of equation, something squared minus something else squared, is equal to some quantity that all observers agree upon, is kind of indicative of, equations like the equation we have for the space-time interval, which, related to the space-time interval to the, components of 4 position. Now, similarly, the equation we've got here in the purple box is actually related to a 4 vector, and it's related to a 4 vector called 4 momentum. A 4 vector describing the momentum of something through space-time, which you can get from 4 position. And the length of this 4 vector, the length of 4 momentum, is equal to the Ross mass of the moving particle. And because, the particle is moving, different observers may disagree upon the amount of energy or momentum the particle has, depending on their motion relative to it, but all observers, agree on the Ross mass of this particle. And we assume that this equation works just as well for tachyons as it does for ordinary particles. But this equation isn't really useful in this form. It's much easier if we rearrange this such that we can work out, if we change the energy of our particle, what happens to its momentum through space. And then looking at what happens to its momentum, we can understand what happens to the speed the particle is moving at through space. So if we rearrange for momentum, we get momentum squared equals energy squared minus the Ross mass squared. So to use this equation, we have to understand what the relativistic energy and relativistic momentum of a particle is. Well, here are the 2 equations for it, where now I have included a factor of c, c squared for the relativistic energy E, just to make it look more like an equation you might be more familiar with. Defining E to be gamma Lorentz factor times mc squared is fine, but to be consistent with the purple equations, we should really go, well, c is 1, so we can just say, well, the relativistic energy is gamma times m. But including factors of c here is really good, because if we go the relativistic energy is gamma times mc squared, well, this looks a lot like E equals mc squared, Einstein's famous kind of equation. And, E equals mc squared is a special case of this. Particularly kind of, say you've got an ordinary particle or an object made up of ordinary particles. Like kind of, let's say you've got kind of headphones, and the headphones are lying on your desk, which is stationary relative to you. So the headphones don't have any velocity relative to you, so we would say the velocity of the headphones is 0. Well, when v is 0, the Lorentz factor gamma, which is a function of velocity, turns out to equal 1, in which case our equation for relativistic energy reduces to the relativistic energy of a stationary object is just mc squared. In other words, E equals mc squared describes the total relativistic energy a stationary object has. But as that object starts moving, obviously it's going to gain more energy due to also having kinetic energy, and therefore gamma increases as the velocity v increases. So that's relativistic energy. Now, for relativistic momentum, it's defined to be gamma mv. Now, it's gamma mv instead of just mv, because as you kind of accelerate an object, due to time dilation, that object will seem to resist more and more any force you apply to it. So it's like that object is getting heavier and heavier in a sense. So it's like its mass is increasing. And so if we say the momentum, the relativistic momentum, is equal to this kind of relativistic mass, which is some function of velocity, then multiplied by the velocity, well, that will still define relativistic momentum perfectly well, but this relativistic mass turns out to be gamma times the Ross mass of the moving object. So in short, the relativistic momentum is gamma m times v. Now, if you would like a bit more detail on relativistic momentum and the kind of four vector of kind of four momentum, then there's kind of the last video on this playlist goes into four momentum in some detail and applies it to some virtual particles and other really wacky type of particles. But for our purposes with tachyons, this is all we need with regards to momentum, energy, and four momentum. Now, gamma is traditionally defined as a function of velocity, but for our purposes it will actually be more useful and more helpful, more easy to see what's going on for the purpose of tachyons, if we define gamma squared, which will indirectly define gamma. So gamma squared is just equal to, by definition, c squared divided by c squared minus v squared. So gamma on our Rank spectra is defined, according to this equation. So before we go any further, it's worth considering what these equations would say for ordinary particles and what they would do if we decrease their energy. Well, due to kind of the equations we have here, well, if v is going to be less than c, so if we're looking at something that's travelling slower than the speed of light, then gamma squared is positive, because c squared minus v squared is positive. And since gamma squared is positive, gamma, the Lorentz factor, is going to be a real number. Hence, the relativistic energy and relativistic momentum are also going to be real numbers. Because obviously, c, the speed of light, and the velocity of the particle, as well as its Ross mass, are all kind of real numbers. So E is a real number, P is a real number, and therefore E squared and P squared are going to be positive. They're definitely not going to be negative. And therefore, if we look at our purple rightmost equation, P squared equals E squared minus M squared, we can go, well, since P squared and E squared are positive, and also M is a constant that all observers agree upon, and therefore, won't depend on the relative velocity of our moving, particle, and therefore, M is going to be some kind of constant of motion, if you like. Well, as if we decrease the energy, it's going to become less positive and get closer to zero, in which case the relativistic momentum will also become less positive and will get closer to zero. And if we look at the equation for relativistic momentum, you can show, well, if the relativistic momentum is dropping, then the velocity of the particle must be dropping. In other words, as we decrease the energy of our particle, the particle slows down. If that particle is moving less than the speed of light, as we would expect, but what happens if the particle is moving faster than the speed of light? Well, then c squared minus b squared is going to be negative, so gamma squared is negative, and you guessed it, gamma, the variance factor, is then going to be a square root of a negative number, so it's going to be imaginary. And this immediately means that the relativistic energy of a tachyon and the relativistic momentum are also imaginary quantities, or put another way, the relativistic energy squared and the relativistic momentum squared are going to be less than 0, not bigger than 0. And that's assuming we insist that the tachyon still has positive mass mass. You can define a tachyon to have imaginary mass mass, but you have to change the other things accordingly. And to keep consistent with this playlist and the material I've covered here, and given we've really built up this playlist principally to describe ordinary particles, I'm going to stick with the convention that mass is real, so mass is going to be bigger than 0. So our tachyons still have real mass mass. So we've got mass is real, and therefore m squared is positive, but energy and momentum are imaginary, so energy squared and momentum squared are going to be negative. And that's going to have a huge impact on what happens to the momentum when we change the energy. So, if the energy of our tachyon drops, we have to firstly define what we mean by it dropping. Now it's easy to define what we mean by the energy dropping or getting smaller if the energy is a real quantity. But if the energy is imaginary, it's not really clear what decreasing the energy means. So to get around this, we go, well, in our equations of special relativity, what really matters in terms of the dynamics, at least the connection between energy and momentum, isn't E, it's E squared. And E squared is at least real, so we can talk about E squared dropping. So when we say the tachyons are losing energy, we mean we're making E squared smaller. It's the best we can really do. But E squared is negative to begin with, so if E squared is getting smaller, then E squared must be becoming more negative. It's getting further away from 0. Well, if E squared is negative, and m squared is positive, then using our equation for p squared in our particle box, we can see, well, if E squared is becoming more negative, in other words, our tachyons are losing energy, at least that's what we define that to be, then the square of the momentum of our tachyon must also be becoming more negative. And using our equation for the relativistic momentum of our tachyon, we can show that, well, if p squared is becoming more negative, then the velocity v of our tachyon through space must be increasing. So in other words, as our tachyon loses energy, it actually moves faster. Really contrary to what we might expect. And also an interesting thing is, there's no real lower limit on how negative E can get. E can get as negative as it likes. There's no lower limit on how negative E squared can get. So E squared can get as negative as it likes, and it can go down and approach minus infinity, implying that then the velocity of our tachyon can approach infinity. So tachyons can't move slower than the speed of light, but they can move a hell of a lot faster. So that's kind of like tachyons and the strange properties. But to wrap things up, I'm now going to summarize our video. But now some of the features of tachyons, and if you watch Star Trek, you'll know what they mean now. Although they use the word tachyon in interesting ways, but Star Trek is really cool, but they do love tachyons, tachyon beams and tachyon reverse pulses, particularly in the Next Generation, are kind of quite popular. But these are some of the cool properties of tachyons if they were to kind of exist in the universe according to our current understanding of modern physics. So now we've covered everything we really need to about tachyons, we're just going to wrap everything up with a neat summary. So here are the kind of three key points about tachyons. So firstly, their kind of definition. Tachyons travel faster through space than the speed at which light travels through a vacuum. That's kind of founding principle of tachyons. Secondly, as you decrease the energy of a tachyon, by which we mean make E squared more negative, then the velocity of the tachyon will actually increase. Very kind of contrary to intuition. But also we saw after the introduction that the roles of time and space seem to reverse in that kind of like when jumping from ordinary matter to tachyons, you essentially flip the space and time axes, or if you like, the space and time components of 4 vectors. And that leads to like linking the notion of extreme time dilation to the idea of momentary tachyon particles. So those are kind of like 3 key things. Now, as for the third one, okay, we don't have any evidence that tachyons exist in the universe, but we do know of a place in the universe, actually multiple places, where the roles of time and space flip, and that's at the event horizon of a black hole. And so I think understanding tachyons indirectly may help us with understanding the black holes, and I think there's actually a lot of physics there to be explored, some of which have been tapped into, but I think it's quite actually promising there, and it's one of the reasons why I feel like tachyons should be taken probably more seriously than they are generally, not because I necessarily believe tachyons exist, but because black holes definitely do, and there's an interesting similarity between tachyons in special relativity and a general relativistic description of the event horizon of a black hole. So these are the three main things. Now, after this video, at some point I'm hoping to create a kind of part 2 to tachyons, which will be looking at how quantum mechanics can come into the picture, but really how quantum mechanics struggles to come into the picture, because we'll see that whereas Schrodinger's equation can describe particles which are moving much less than the speed of light to a good approximation. So Schrodinger's equation can in many cases actually describe ordinary matter pretty well. Schrodinger's equation completely breaks down almost immediately for tachyons, even in the simplest case of a freely moving tachyon, and that has to do a lot with quantities that we consider to be real for ordinary particles becoming essentially imaginary for tachyons. So it's a theme that continues into quantum mechanics. But that's just everything for this video. If you enjoyed learning about kind of like wacky areas of kind of modern physics, things like tachyons, time and space switching rules, black holes and all that kind of thing, recommend kind of like subscribing and hitting the bell icon so when new videos are coming, and and I hope kind of like there's kind of other videos on this channel which if you enjoyed this one will hopefully be a benefit to you too. But that's everything from this video. I usually towards the end of a playlist will try to put some challenges at the end to encourage kind of more thinking and kind of like reflections into kind of some of the material for those of you who would like to have some guided direction in kind of how to take the material covered here further are kind of like, step to kind of help with the great venture of physics, as it were. But I'll probably save that for part 2 after we look at kind of how quantum mechanics seems to really break down, at least non-relativistic quantum mechanics for tachyons. Well, then we come to the end of this video. Hope you have a really good week. And as always, I hope to see you for another video soon.